You solve intelligence, we're done. The whole human race can go on vacation now, right? There are certain things about Neuralink that are tough. The material science behind Neuralink is tough. Like getting a level of biocompatibility and getting the insertion procedures mature to the point where we have no qualms about putting this in perfectly healthy human beings. Like my experience with how those kinds of techs get developed is they take time because we are very cautious in how we develop that stuff. If we had mature nanotechnology, brain-computer interface is trivial. Like it becomes a very simple problem.
I had the privilege of speaking with James Douma, a self-described deep learning dork. James's experience and technical understanding are not easily found, and I think you'll find his words to be intriguing and insightful. This is one of several conversations that James and I plan to have. The first conversation was recorded earlier on our channel, so check that video out too if you haven't seen it. Hope you enjoy this one.
Let's talk about ChatGPT and pairing ChatGPT with Neuralink, and like, what does the future look like with a version 10 ChatGPT with a version 10 Neuralink?
Well, so I think there's a stage of brain-computer interface development where the thing you want to plug into is the language center, right? So ChatGPT, it's based on a large language model. It processes like these are sequence models. They don't have to be just sequence models, but they're mainly sequence models. Sequence models, basically, they take a sequence in and they generate a sequence out. And the mapping can be arbitrarily complicated. So, if you think about it, if you have a sufficiently sophisticated input to output sequence converter, if it's sufficiently sophisticated, you can ask it any question and you can get the answer. What is a cure for cancer? How do we travel faster than light? Like everything can be expressed as a sequence, both input and output. So language models, they just process sequences, but we've gotten them to this level of sophistication that they're starting to knock on that door of being able to answer your questions, whether the question posed is a unique riddle or whether the question posed is just a factual inquiry, right? And so that's where we are right now with ChatGPT. That gets a lot better. In a sense, if you pick up a phone and you talk to a human being, that's a sequence input-output thing. So, imagine you could call God on the phone, right? You can ask him anything and there's nothing he can't answer, right? So that's like a sufficiently advanced version of ChatGPT. And the limitation becomes the fact that you have to just talk, right? If you want it to learn geometry, but you can only talk to your professor on the phone, there are certain limitations. There's certain things that you want to describe by drawing something on a blackboard and pointing at a picture, right? There's just a lot of stuff that's expressed that way. There are lots of other things. So right now, at the level of human input output, we got 5 senses, and we mainly use 2 of them, sound and vision, to learn almost everything. Those are the really biggies. So ChatGPT sort of works with abstracted sound. It works with language. There's nothing to prevent you from building a version of ChatGPT that takes audio in and produces audio out. I'm sure we'll see that really soon. And you could hack together a voice interface, and people have already hacked voice interfaces onto it. But actually building a version of ChatGPT that takes the audio, because it's not well appreciated, but you can't actually write human language down. The thing, when I say something to you and you write it down, there's a huge amount of stuff that get like that huge, like you don't write that down, right? It doesn't get there. The nuance, the posing, the pacing, the body language, there's all of this stuff that doesn't get in there. And when humans speak to one another, all of that carries a lot of meaning. That's why a lot of people don't like remote work, because they're the kind of people where the body language really matters, and they want the full fidelity of it. I really like video over audio calls for the same reason. I'm on the spectrum, and it's really hard for me to detect a lot of things in speech. And if I can see your face, I get a lot more out of the interaction than I get if I don't have that. So, vision adds a lot. But then there all of these additional layers of things that we have in our head for talking to ourselves and explaining things to ourselves. For instance, there's all of these nuanced levels of emotion. We have how many words for emotion in the English language? I mean, hundreds and hundreds of them. Melancholy, so melancholy is a feeling. You learn how to map the word melancholy onto what you understand to be the experience of melancholy by reading other people's descriptions of experiences of melancholy. And so but melancholy, it's not a single thing. Like, melancholy is like this 50-dimensional thing that could, it could, on the one hand, it could, you have the nostalgia aspect, there's this nostalgia aspect of it. Then there's a sadness aspect. There's all of these, things that go on, but we just have the one word. If you could break out all those words, like if we could communicate in that space of all of the subcomponents of emotion that go into that, well, now you've got this other layer of communication that you can do. So language is easy in the sense that we know that language is already an abstracted representational form. And we already have a lot of pretty powerful descriptors for it. And we already have a lot of powerful tools, even AIs that can work with language, either in voice form or in text form. So to me, it's a natural, like by the time we get to where we have Neuralink, I don't think we'll ever go through the keyboard and mouse phase with Neuralink for normal, healthy people. That's where we'll start in the early days for quadriplegics who need an output, because it's the first really useful, completely general thing you can do. The bandwidth is just really low, but there are advantages to low bandwidth that make it easier to implement it. But we're very likely to get to a level of maturity of the technology before we start talking about putting it in healthy people, where you can just go straight to the language interface, so that you've got a 20,000 or 200,000 word vocabulary, and you can speak at 100 words a minute or 200 or 500 words a minute. So you just get this fantastically higher bandwidth, like right out of the gate for healthy people. And because language is so well established already as a communication medium, like it's the practical place to start, but it's not the end of the game at all. Language, like human language is amazing. It's just a really, really powerful tool, but it's still talking through a straw compared to what's going on inside your brain. There's so much going on there that you cannot share with other people because the pipe is too small. And Neuralink has a potential to break open that pipe. And if you want to break open that pipe, you have to move away from language as an encoding, because language was developed for this ultra low bandwidth interface that we have between each other. And if you really want to get past it, you have to step outside language as a medium that you do. And I expect, like, we'll go to that we'll go to representational systems that are higher dimensionality than language and higher bandwidth than language relatively quickly, long before we do the full brain interface type thing.
I see. And so in between, like ChatGPT or that really long-term interface, there's kind of the in-between, which is the audio ChatGPT, and then there's also the video ChatGPT.
Well, an interesting question is whether we'll get to, thought ChatGPT, because, we, like human beings experience time sequentially, right? And so your brain iterates through, your brain is a state machine that has a lot of sub-elements that have their own states, but you can describe the brain as a system that has a lot of hidden internal state that evolves in coupled and independent ways. Yeah, like you could describe the entire brain as a single state machine. That's a very complicated internal state. You have a latent variable, which is your thoughts, which is embedded in you. Like your internal experience is a latent variable that's embedded in your experience of reality. And you could give GPT access to that. So it could take that thought, that latent reality variable stream, process it, and then hand it back to you in that format, right? That's probably the highest level of sophistication of an interface that you can get to with a human brain, a biological human brain. So, that's the end game, right? That's where you get eventually. And, somewhere way down probably around the time that we can first start doing, Neuralink in healthy human beings, you start with the language interface, because it's the super appealing low hanging fruit apple right there on the branch for you. Because language is like, it's going to be a great place to start with this, but there will be things past it, like way past it.
If I understand what you're saying about a state machine correctly, then you could manipulate like your feelings of time too, right?
Yeah, let me explain that terminology. It occurs to me. Maybe a lot of people don't. So there are machines that have where in order to get them to do what you want, they have an internal state which represents they have an internal state which changes over time. So like your microwave oven, it has a controller that's a state machine, and the states are just sitting on the counter doing nothing. There's definitely a state where, like, I'm currently microwaving your food, and aspects of that will be like, this is the power, and this is whether or not the light is on, and this is whether the turntable is turning, right? These are aspects of the state. At any instant in time, you could describe the most important features of it in one or more variables that are its state. That's what it's doing right now. When you write software to control a microwave oven, you frequently write it in the form of a state machine where, given, you have a bunch of if then else, whatever things that are basically, if I'm in this state and this thing happens, my next state is this one. So, like, you could be in the state of microwaving, and the state machine could say, if I'm in the state of microwaving and someone opens the door, the next state is not microwaving. And that's how it transitions from microwaving to not microwaving, right? So it turns out that most complicated things that we build in the real world as engineers and programmers, to some extent, you can represent them as state machines, where they have an internal state. Your computer is a state machine. Like most of the software in your computer desk could be thought of as a state machine. Certainly the control aspects are, car controls and stuff, they're state machines. The car has an internal, state, which is, I'm going this fast, my steering wheel is at this angle, the brakes are not pressed, these seats are occupied, the heater is on. You've got all these variables that describe the state, but the totality of all those variables are the state. And the control system of the car, has a bunch of mechanisms that examine one or more of those state things. And then, given that you're in a certain state, they interpret a stimulus as requiring them to transition to some other state. And that other state might have the airbags go off, or it might have, the door light turn off because you closed the door or something like that. Like, these are all state transitions. So in the extreme case, any arbitrarily sophisticated machine can be described as a state machine. And a human being is one of these things that could be described as a state machine. So what's the state? The state is, when you write a piece of software, you have this data structure inside it, which is the state, where, the parts of the software that are deciding what to do when a stimulus comes in, they look at they get a stimulus, they look at the state, then they look at this table that says, if I'm in this state and I get this stimulus, then I go to this state. And when you do your state transition, then you change your inputs and outputs, all the things you have control of, to match the new state, right? It's a really powerful way of thinking about control systems, and it gets used almost universally for okay, so that metaphor is also used in machine learning. So ChatGPT is a machine. It takes a sequence input. It has this internal state variable, which it generates from using a neural network. The neural network says, here's my input sequence, here's my internal state. We call it a latent variable. It's called latent because it's hidden. You can't see the state. You can't interrogate the state directly from outside. Only the software itself can interrogate the state and change the state, right? So it's this variable that's embedded inside the thing. But that variable encapsulates the entirety of the reality of the software, right? Like, everything is embedded in that. So ChatGPT, like many, many AI programs, it takes the outside world, converts that into an internal state variable, and then that state variable will be reflected in a particular set of outputs. And when you get another thing, like when you get the next word in the sentence, right, it takes that word, it looks at the current internal state, which will include the history of all the words it's seen up until now. Like, how do I interpret this word? It's the context for its interpretation. And then its new output is generated, is stimulated based on the new word added to the existing context. And the state is updated to, the state plus this word I just got, right? So that's the latent variable. So if you apply that concept to a human being, what's going on inside your head is your state, right?
I see. Okay, thanks for going through that. I have some other questions here that are not so related to what we were talking about, but I think they're useful in understanding like the architectural decisions that Neuralink has made and their like broader goals for planning and scaling the device. So initially in 2016, Elon did an interview with Kara Swisher and at the Recode conference, and he was initially saying that one way of doing a brain interface is going through the vasculature, and you don't necessarily have to do a surgery. There are plenty of other companies that are working on wearable devices to get some sort of brain data. And then there are other companies that are pursuing that vasculature network implant inserted device. But then Neuralink is obviously doing this pretty invasive implant. Can you talk about the pros and cons of all of these?
Well, so stent, the inserting something into the vasculature, the way there's a company right now, I think they're called Stentrode. I think you might have talked about them once before.
Yeah,
so
Synchron. They have a device called
so they have like 16 probes on the end of a stent. So stents are things that it's a medical technology has been around for a while. You slide this sort of tube made out of wires into a blood vessel. Stents were originally developed to help with people who had clogged arteries in their heart. So you can slide a stent into a clogged artery. You can twist it and the wire cage expands to hold the artery open. So you solve clogs that way. There are kinds of stents that can be inserted into the vasculature in the brain. You can insert a stent almost anywhere if the blood vessel is significantly. You just, it's on the end of a wire. You insert it into a blood vessel, and then you can just push the wire until you get the blood vessel where you want. They have a little, set of controls on them so that you can cause the tip to bend left or right or something. You use an X-ray machine or an ultrasound to visualize the tip. And as you work your way through the vasculature, you steer it to get it to whatever part of the body you want. Of course, it stays inside the blood vessel, but blood vessel walls are pretty thin. And if you're going into the brain, compared to a non-invasive system that has to try to, extract signals from neurons through the skull, being separated just by the membrane around a blood vessel, obviously it's getting you a lot closer to the tissue. It doesn't give you quite as much flexibility as direct stuff does, because you don't have big blood vessels everywhere in your brain. You only have so many. The vasculature tree, the branches are thinner and thinner. The stent can only go down so small a branch. Existing stents, they can't go into really, really small blood vessels. So you do end up being kind of restricted in terms of like where you could potentially put that stent. And so you're not getting exposure to a really large amount of tissue. You are getting pretty good exposure. Now, the big upside to it is that the surgery associated with the stent is a relatively simple surgery. I mean, you go in, it's a local anesthetic. They slide the thing into you. You're out in an hour or whatever. In the case of using a brain-computer interface, the end of the stent, there's a electronics package that goes on the end of the wire on that stent, and that's also planted inside the body someplace, right? But in a lot of ways, it's a much less invasive surgery that and potentially entails significantly less. It's not risk-free because stents can damage your blood vessels. They can cause blood clots. Like that's the single biggest thing associated with stent. Like your body has a response to the stent. you get clots. Blood clots can be bad, especially in your brain. So they're not entirely risk-free, but it's considered relatively low risk compared to cracking your skull open and implanting something. So it's kind of an intermediate, it's not non-invasive. I guess you'd call it less invasive. And less invasive means it's going to be kind of an intermediate between the strengths of, the strength of a non-invasive thing is you can take it off, you're not going to get an infection from it. There's no immune response to it. There's all kinds of things. The downside of non-invasive stuff is, your brain is encased in a protective structure, which is very thick and very durable and not at all amenable to transmitting signals to the outside world. So you don't get a lot of signal resolution in either time or space when you are trying to talk to the brain through the skull. And that's a huge limitation. It definitely sets a pretty low upper bound on the level of functionality that you can get out. Like you're not going to get, I guess it depends on what signals you're pulling through. Like fMRI is non-invasive. And fMRI can see a lot of details inside a brain. Like you can get down to, I think they're down to like 2 millimeter resolution or something like that on fMRI now. So you can see pretty small things. And potentially you could get a lot of data out of that for a very highly trained individual who learned the biofeedback techniques necessary to, express themselves through an fMRI machine. So like in some sense, there could be some potential there eventually. But people have been looking at that for a really long time. And the amount of bandwidth that we are likely to get in the foreseeable future through non-invasive stuff is really quite low. Using a stent, going through the vasculature with stent technology that we have today is potentially significant improvement over non-invasive stuff. But like you can't compare it to Neuralink. Just like the difference in bandwidth is just enormous. Like what they will be able to do with Neuralink, like right out of the gate, is just going to it's going to blow way past what you're theoretically ever going to be able to get out of a system which is built using current stent technology. Now, I think Elon mentioned this concept of a neural lace, which has been around for a while. It was like most of the people who talk about it right now, there's a version that the same author that wrote the books that Elon names all of his drone ships out of. Who is it? I forget. Anyway, so
I haven't read it, but is it Isaac Asimov?
No, it's not Asimov. It's I've got all his books. You'd think I'd remember his name.
That's good.
This is what happens when you get old, right? Anyway, the idea is at the extreme end, it's a nanotechnological device, right? So you have something which is inserted into a blood vessel. Like if I have arbitrarily good material science so that I can build a web that uses like single molecules for wires, that it can grow itself. It's got sophisticated processing all throughout its structure. And you can get down to like single molecule scale for the web itself. You can build something that can go through the capillary network in the brain. So like, capillaries are the smallest blood vessels. Like you go through the vasculature tree, and at the far end, you get to these minimal size tubes. And they're the minimum size because they're just barely big enough for one blood vessel to squeeze through. Like you can't get any smaller and still pass blood. So that's a certain scale. That's a capillary. And that's those are the finest things. Well, the capillary perfusion, the number of capillaries you have per cubic millimeter of tissue in your brain is incredibly high. So if you can build an interface that can fully exploit the capillary system of the brain, you can get like Neuralink you can get something that has the kind of resolution Neuralink has without having to go do anything invasive at all. Like, so there's this, concept for something that could be made if you had high enough materials technology that you could inject a neural lace into like the carotid artery. It could deploy into the full capillary vasculature system of the brain, and it would give you access to all of the brain, the deepest levels, and it would not require any surgery beyond, injecting it into the vein. So, there's we're really, really far away from being able to do something like that. Like, it's crazy. It's a crazy high technology, but it's kind of the holy grail if you can do it. Like, if you have the material science to be able to pull off something like that. Short of that, the second best thing is basically doing, what Neuralink does, except, ideally a much more refined version. If you can get down to the single molecule wire type stuff, then, even doing something like Neuralink is like what you can achieve goes way up. Like, you could connect to every neuron in the whole brain, right? If you had that technology and you're willing to go invasive.
I see. Formerly, Neuralink was doing multiple holes with a pill behind the ear, or a pill-shaped device behind the ear. I'm going to show you a picture of this. Let's see, share my screen. So this is what it used to be. And can you talk about the improvements that have been made and the advantages of changing it to how it is now?
So the advantage of the old, you can see why the attractions of the existing system are the incisions that you're making through the brain. You don't have to remove as large a chunk of the skull, but you do have to go through the skin. And so, like any place in the body where you have something that has to go transdermal and stay there, there's a potential for infection. There's a potential for injury at that site. So if you're transdermal the way that this thing is, you do have those problems going like through the skin, worrying about infection, that kind of stuff. They also have this, if you have something external to the body, the potential for mechanical damage to it, it being bumped, you're having an accident, you have a fall, you put on sunglasses, that, like, all of those things potentially can damage a device. That's less likely for something which is entirely internal to the body. But in this case, you get to make much less invasive incisions in the cranium itself, and you can distribute the electrodes more widely. Like, one of the disadvantages of Neuralink in its current incarnation is, you've got something roughly the size of a quarter, and that's kind of the largest area of the neocortex that you can span so you couldn't like plug into the visual cortex and then also plug into the language center, because they're too far apart. You need two neural links in that situation. Same thing with, like, your primary motor cortex is too far from your language center. So a single neural cortex wouldn't be able to do both of those things. With this, you could potentially do that. I think the downsides of this are the signal integrity is going to be a lot lower. I don't know if the plugs they have in the bone here include electronics, but I think they do not. So basically, you have a passive transmission line going from the active electronics, which is behind the ear, and the length of that transmission line is going to be a problem in terms of the number of channels that you can transfer and the signal fidelity that you are going to be able to get. So basically, the version that they're doing now is more invasive and somewhat more risky, but it has dramatically higher channel capacity. That's probably the trade-off.
Sure. And then can you discuss the pros and cons of Bluetooth versus, like, maybe some sort of other alternative?
So Bluetooth is pretty good. Low power Bluetooth is what they're using right now. If you were going to pick something that you were going to develop, especially for Neuralink, you'd probably make some changes. You could like for example, Bluetooth is designed to transmit at higher power for much longer distances than Neuralink really needs. You don't need to go that far with Neuralink. Bluetooth probably doesn't have the bandwidth that you want. You probably would like lower transmission power, higher data rates, and maybe go for a protocol that takes less encoding, so there's less heat generated as a byproduct. Because that, like, one of the problems they struggle with is heat generation approximate to brain tissue, which is not good. You could also pick a wavelength that was maybe better for transmitting through the body. It's I guess 2.4 gigahertz that they use for Neuralink isn't bad. There are better frequencies that you could pick. Overall, I would say Bluetooth it's not bad. Certainly, like if you're going off the shelf, it's got a ton of great things going for it right now. But if you were going to develop something from scratch, you would probably pick something a little bit different. And I expect they probably will go to something different. The thing about Bluetooth right now is it goes straight to your phone because the phones all have it. Like, that's a huge piece of low-hanging fruit. If they go to anything different, then they'll need a peripheral we'll need to wait for Apple to come out with the Neuralink peripheral for their embedded in the phones.
Mm-hmm. Let's move to Neuralink clinics. So Neuralink is aspiring to convert from just like their current prototype to a mass delivered product. So with the clinics, what would those entail? And is it fair to compare that to like the Tesla showroom model versus being part of the whole dealership network?
Man, that seems pretty far away, doesn't it? Well, long term, they want to be able to do Neuralink the way we do LASIK today. LASIK is, it's mostly an automated surgery. You go in, you go through your pre-op, you've had an exam before you go in. And a robot performs the surgery, and it takes, I don't know, seconds or something like that. And they're really accurate and they're really safe. So I imagine that long-term, that's what a Neuralink clinic in, I don't know, 2050 or whatever, maybe that's what it looks like. Is it's a total outpatient procedure that takes 30 minutes. It's all done by a robot, and the setup all gets done ahead of time. I think the Neuralink, the clinics that they're setting up right now, they're setting up operating theaters that I am expecting are, in the short run, they're going to be optimized for working on animal subjects. And it looked like they have a setup for spinal implants and a separate one for cranial implants, where in certain respects, like the cranial implant is actually the much simpler procedure, I would imagine. But they probably do a lot more of those right now, and they probably will continue to do a lot more of those than they'll do the spinal implants. When you move to humans, I would bet that early things, like, I wouldn't be surprised at all if they end up happening in hospitals, like with full-on, cranial operating theaters and whatnot. And then, as they get more experience with it, they're able to transfer it to a less sophisticated, more outpatient-y kind of facility. But I would expect that to take a while.
Okay. Timeline. So how long do you expect it will be before we're able to download our minds onto a Tesla Optimus bot, or even like 1,000 Optimi?
Yeah, it's man, the download thing, there are a couple of different ways to get there. If you were trying to do it short term, you need an interface at least to the large majority of the neocortex. And that's a pretty invasive, that's like, a Neuralink the size of the whole top of your skull, basically. Yeah, it's the whole, so that's a lot. You can do an approximation to that, where you look at a lot less of the brain, and then you use use algorithmic systems to predict what the other part must be, but the fidelity of that copy is going to go down if you do that. And probably the most significantly, like the experience of the user would be that they were being copied, not that they were transferring, right? So the other way of doing it is you get the full interface and you get plugged into an external AI, and over some period of time, your experience of reality becomes split between your biological body and the external system. And in that case, the experience of the user would be that they would gradually transfer into that external vessel. So in certain respects, that can happen sooner because you don't need as much of a brain interface, but you need a lot more external hardware. I think the external hardware is probably going to mature faster than Neuralink is over the next few decades. So I would guess like there's a pretty good chance that that ends up being, like, to the extent that people end up occupying non-biological bodies, I would guess that's somewhat higher probability pathway right now. And how long will it take? Like I like it. It's decades away at least. Like it doesn't happen super soon. But in an interesting way, Neuralink is probably the rate limiter on that, because I think, there are certain things about Neuralink that are tough. The material science behind Neuralink is tough. Like getting a level of biocompatibility and getting the insertion procedures mature to the point where we have no qualms about putting this in perfectly healthy human beings. Like, my experience with how those kinds of techs get developed is they take time because we are very cautious in how we develop that stuff. So it tends to proceed. It could go a lot faster, but because it's a luxury device, at least for now, right? Like, people, we're going to have to see how society evolves, right? And we'll have, like, a thing that could happen is if there becomes this perception that the AI really is an existential risk, maybe it gets higher priority, right? And we decide that we're willing to take a certain amount of risk, or if the economic benefits of getting it are sufficient, and that there are people who, really want those economic benefits, then, maybe it becomes one of those things where, you go to Guatemala and you go to a black clinic and you get it done there. Like in, William Gibson's cyberpunk novels from the 1980s, right? Both of those probably happen faster than the FDA approved approach, where we have to wait for 3 generations of doctors to die off before, some super invasive thing gets approved for general use by the public over the counter. Right. So, I mean, like my biggest concern about how fast it can happen is not how fast the tech can mature. It's more about our regulatory apparatus. And, if you asked me to like go get a Neuralink today, I'd like, no, it's like the risk reward trade-off is just not there today for that kind of stuff. And we got a long way to go before perfectly healthy people who are in their right mind are going to sign up for having a procedure that invasive done for the benefits that you're likely to be able to get in the short run. If I can talk to my phone, I can text, I have voice, like we're going to have voice rate communication with sophisticated AI really soon, even without Neuralink, because AIs with arbitrarily good, verbal skills, they're in the near future now, and we get those by talking to them. What Neuralink offers you is the ability to go way beyond that, and it's going to be a little while before those interfaces where the physical interface is mature enough that you have a lot of people signing up for it, and because that's a precursor to developing the software backend that gets you the really good, access to higher level cognitive functions. So both of those take some time.
When you were discussing having like part of your own brain or your own feelings staying in your own biological body and then some being in the Tesla bot, what if you had like 5 Tesla bots? And
if you have the external hardware to support it, then it works. One of the most amazing things to me, like I remember back in I think it was it the late 80s or early 90s, the first time that they did an experiment where they, God, I wish I could remember this guy's name too, because he really deserves a lot of credit, but essentially hooking up a primate motor cortex to a robot arm and saying, if a primate could learn to control the motor cortex. And there's this point in the experiment where the primate has learned to control the third arm, right? Which initially in the experiment, you're mapping the primate is learning to control the external robot arm using the same set of motor neurons it uses for one of its actual biological arms. But as the interface becomes more sophisticated, the primate can use all 3 arms simultaneously, right? Like initially, the interface tries to mimic one of his biological arms, but as the primate learns more and gets more control, eventually he's got 3 arms. So think about that. We tend to think of the human brain as, and this was certainly true at that time, like that experiment hadn't been demonstrated before, that there was reason to believe before we saw that level of work, that the capacity of the human brain was so tightly mapped onto the physical characteristics of our bodies that there was no reasonable mapping to a different body configuration. Like a third arm is a different body configuration, right? Mm-hmm. It's like there were reasons to believe that we just weren't going to have that level of plasticity. But what we've learned since then is the neocortex is not tightly wedded. The neocortex itself, the white matter is very tightly wedded to the configuration of the body because it's the cabling that connects your neocortex to your body, right? But the neocortex itself is not super tightly wedded to that. So like, you could have more eyes, you could have more arms, right? You could have a second body, right? That the neocortex it's not, we don't have hard limits there. Now, we do have a hard limit there's an upper bound of the amount of processing that you can do with your biological brain, right? There just is. You've only got so many neurons, and it takes a certain amount of processing to do all of the, say, motor functions that go on. But, if you take the motor function itself and you export that to an external system so that the external optimist that you're controlling, like there's a brain in the optimist that's doing the motor cortex parts of it. And the high level representation that's getting exchanged is much more abstracted. That's still like, if that external abstraction has to come back to your biological brain and get processed in your biological brain, along with all the representations you're getting from your physical body, there's going to be a certain amount of interference, and you still have some limitations, right? At that point. But you do, in a sense, get to occupy 2 bodies at the same time with maybe 2 sets of senses, 2 sets of motor skills, and that kind of stuff, right? We don't at this point have a good reason to believe that that's outside the set of capabilities. Now, what that would feel like, I have a really hard time getting my head around it. Like 4 eyes, or being able to see out the back of your head. Like, what would that be like? That would really mess with your sense of space. And, like there's a level at which that's possible. Now you take the next step and you start taking some of those higher level functions and you export those too, right? So not only is the motor functions, but some of the high level function processing functions are also exported to to the Optimus. Well, now you are you, and you are the Optimus robot, or the 10 Optimus robots, and you've just got like this sort of weird telepathic link where you're all sharing each other's sensations, and you're operating as a hive mind to decide what you're going to do collectively. This is getting really weird, isn't it?
No, I mean, it's weird because
we're talking about what's possible, right? We're talking about what's possible here. This is, I mean, will people do this? Like, it's going to depend on it's a path dependency. Like, which technologies mature at which times, which ones do people decide to adopt, what gets prohibited, what gets encouraged, what's cost effective, what's not. All of these things are going to influence the shape that these technologies take when we finally get them.
Yeah, I see. I think Neuralink could do something so similar to what Tesla's doing with their artificial driver. Like Tesla's basically taking all of their fleet data from the biological drivers, and all of they're basically using everybody's driver brain to recreate their own Tesla artificial driver. I suspect that Neuralink would be able to do something really similar if they have Neuralink implants in millions of people, and they have like everybody's brain feeding this artificial brain, and then all of a sudden, like, you sell this artificial brain to everybody, or you license it as a software package. Does that seem feasible to you?
I have to like put some rails on this description to sort of make it match up with my understanding of how this stuff works and what the technology, the way it works today. So, I mean, there are a lot of ways that Tesla's autopilot team uses the fleet to help them develop FSD technology that can drive the cars. Lots of different ways. The one that most people think about is the way the cars are used to gather training data that can be used to train neural networks that are used for perception, contextual awareness, planning. They're starting to use neural networks for planning too. That's not the only way. There are lots of ways you can use the fleet, right? You can use it to test run, like in shadow mode or not in shadow mode. People who use FSD, they drive the technology, they're testing it, and they provide feedback in real time as they're using it, because every time they intervene or they correct it or whatnot, they're adding a signal. They're identifying a circumstance where the behavior is inadequate and it needs to change. And, the big data backroom machine learning processing that they do on all of these examples, because they've got, hundreds of thousands of people using the system. So they get a lot of detailed statistical data about where the system performs well, where it doesn't. And they can close that loop of, training the system to get better so that you have fewer interventions. Okay, so that's kind of the course thing, that is going on. So if you have a lot of people with Neuralinks, can you can you do an analogous thing to the thing that I just described? So the thing that I just described is not the only way that they use the fleet to create the software. It's just the most kind of notable one that most people talk about most generally, which is like gathering training data and then using the fleet to evaluate the current state of the system with kind of detailed feedback. Could you do that with a Neuralink? Sure. If you have a function you want to add to a Neuralink, or you have some external system that you can get a bunch of people to interact with, you can gather data from their interactions and you can use it to refine the behavior of the system. ChatGPT is doing this right now as one of the training. The way ChatGPT gets trained. ChatGPT is a GPT transformer neural network that's a language model, which is actually really similar to GPT-3, which was a previous generation. And the biggest difference, the thing that added all of the amazing capabilities to it recently, is that they changed the way that they train it. Well, in the last stage of training, they added these additional stages of training, but one of them is reinforcement learning from human feedback. And when they want to do the reinforcement learning, they train the system in a sandbox to produce useful answers. And what constitutes, they need lots of examples of useful interactions with human beings in order to build this reference system that they can use for doing this training. Where do they get that data? They're getting it from you. If you're using ChatGPT right now, and it's in the disclaimer when you sign up to use it. They capture that data and they use it to train it and make it better. So a lot of, Google, this is how Google searches get better these days, right? Part of what happens when you type something into Google is stuff that gets processed through a neural network, and they look at how people interact with Google and they gather that kind of stuff. So on that level, yeah, sure, you could do that with Neuralink by, essentially having functions that you're trying to train and using user interactions with Neuralink, or probably more likely, people interacting through Neuralink to some other system, and that other system being the thing that you're trying to make better. Well, being able to monitor the stuff that's going back through between people using their Neuralinks and that system is going to be a super valuable vein of data to tap in making that external system work better for people.
Because you're able to understand how easily or how difficult it was for somebody to understand something or use something.
Yeah, there are lots of ways, actually.
Okay.
There's not like a single thing. It's just, if we picked one external hypothetical system, then we could talk about, hypothetically, like what you get out of it. The fact that there's a lot of data and that you're observing this complex interaction that needs to be refined in a non-obvious kind of non-linear way, like having access to that data is really useful. And Neuralink would definitely provide a lot of that data. So there are lots and lots of ways that you could use it. Like, it's hard to narrow it down to just one. It's kind of what I'm saying.
Sure. Yeah, I see. But yeah, I mean, I think that's, to me, like the most exciting thing about the longest term future of Neuralink is like Tesla with Optimus may be able to use a lot of how they view, literally view the outside world and then work off of that. But then Neuralink would be much more detailed, I think, because you're just recreating what a human would do and what they're thinking anyway.
Yeah, depending on what you have access. This is going to be a really interesting world when we get to that. There are a lot of really foundational concepts that our society is based on that they're not fundamentally true. They're true in the world that we exist in right now. And when things, when the technology starts challenging those, like free will, it's like in a world with Neuralink, that whole question of whether people have free will, it gets a lot more complicated than it is right now. Right. We just we build our world with rules, assuming people have free will. We know we have a long history that if you build society that way, things work better. Right. No. So whether people actually have free will or not is a completely separate issue. Like, you've got to build the world so that they do. But what happens when you start to get these things where they clearly don't? Right. We already have a struggle a lot with mental disease, addiction. We have all of these phenomena that where we have to start asking in those particular situations, do these people have free will? Do we need to treat them as if they have free will? Like, do we need the same incentive systems for them that we do for full-fledged, normal, sane human people operating normally in the world? Because in many cases, you have to change the rules for those people one way or another in order to have a functional relationship between them and society. And in a Neuralink world, you get a Neuralink, you can flip on the happy switch and go sit in the corner. You're happy, right? You don't have to do anything. Does that person have free will? Well, they did when they turned on the happy switch.
Yeah. Yeah, exactly. Like they chose to get in the first place, most likely.
Yeah. But I mean,
99%.
you can say this about alcoholics and drug addicts and right too, but then, you know, you do get, it does, it is going to create these situations, right? And the thing about a thing like Neuralink is it's a much more complicated and nuanced thing because you have a much finer control. Like most of the issues with addiction that we have is people have one or some basic set of needs that are getting met by their addiction, you know, and we sort of know what the substitutes for those are and the mechanisms behind that kind of stuff. But with Neuralink, you know, you kind of have, there's an unlimited number of things that could specifically in groups be satisfied or not. Like the thing I was saying about how, like, wouldn't it be great? You know, I don't know if it would be great. It might be terrible. If, you know, if there were a lot more people like Elon, right? Who are like, you're not satisfied with success. Well, Neuralink, we can make them all that way, right?
Yeah.
Do they have free will? Well, did they decide they want to do it? You know, if you live in a world where you feel like everybody should be, you know, a pious Christian, you know, that's a thing. You can Neuralink, you can make them all pious Christians, right? Did they have free will? If they chose it, it. There are some super dystopian sort of angles to this when we because a lot of the boundaries of what constitutes a human being, where you're going to start crossing those lines, right? Everything having to do with the definition. This is why abortion is such a difficult topic in the society that we live in, right? Because at some level, you can see it as a definition of like, at what point is a fetus a human being? And do we have to treat it like a human being? And people argue, they disagree about where that boundary is. And the disagreement over that boundary leads to us to this really fundamental schism between the two sides in that argument. And that's, you know, that's just, are they, or like, you know, do people have a right to commit suicide? You know, if you got a terminal cancer patient, like this is another thing we struggle with. Like, what rights do people have over themselves? People don't have unlimited rights over themselves, and we don't have unlimited rights over other people. And so, you know, society doesn't have unlimited rights with respect to us. And as long as we're all natural biological human beings, that's a much more constrained discussion. With Neuralink, the number of different dimensions upon which we can disagree is just going to explode.
Sure.
So that's another answer to Warren's question, by the way. You know, how could it destroy us? Is, you know, any sufficiently large change to the collected common sense about what constitutes the relationship of the individual to society and their rights with themselves and society's rights with respect to us. Like these technologies, both AI and Neuralink, in some like really visceral ways, it challenges a lot of those, a lot of truths that have been foundational to human existence forever.
Yep. Tom asks, is the exploding rate of change in AI developments a positive or negative for Neuralink?
For Neuralink's ability to achieve its objectives, it's definitely going to be a positive. Neuralink in particular is interesting because they aspire to have a lot of electrodes placed in tissue, and making the most of interpreting what you get back from those electrodes is a really complicated information processing problem. And it's really well suited to what neural networks in particular, but, you know, artificial intelligence techniques in general are bringing to the table. So improvements in that technology are going to directly reflect in, in the post-processing algorithm's ability to make the most sense possible of what the implant can get from the electrodes that are in there, for whatever number of electrodes there are. If you only have one or two electrodes, there are lots of, kind of traditional signal processing techniques you can throw at trying to understand if one or a small number of neighboring neurons is firing or not, because that's kind of the level of information that you get. But say, for instance, that you are planting a set of electrodes in like the speech centers of the brain. Right? And what you want to get out is, you want to generate words, you want to generate language. And so that's going to be a very complicated function of what the electrodes are reading. And it's going to be very fluid. It's going to change over time, right? So which adds this extra dimension of complexity to it. And AI techniques are going to really help a lot with being able to make that work. So in that sense, it's a big advantage. Now, there's this thing that we talked about a couple of times, which is Elon's aspiration that Neuralink becomes a hedge against humanity losing control to intelligent AIs running various aspects of our society, because it's likely to be the case that at some point we're just not going to be able to keep up with them, at least not as individuals. And so having Neuralink as a way to expand human capabilities to try to keep up with the machines as they get better at this kind of stuff. Well, in that sense, it's kind of working against, that particular goal. The faster AI goes, the sooner the deadline for Neuralink to make a big difference, occurs. And we can hope that Neuralink comes together quickly and shows results for, say, people who don't critically need it. It's probably already efficacious for some population of patients that that have some very difficult trade-offs in terms of their what their injuries or their diseases are doing to their lifestyle. But if you want to get Neuralink to a point where it's a clear benefit for a healthy human being, that's a lot. There's a lot of road that's got to be covered between here and there. And you probably have to get past that before Neuralink starts to become a hedge against the potential for too powerful AIs in our world. So like in that sense, I guess, overall, I think it's a big win. I think you probably couldn't do Neuralink without AI that we have today. Like if you rolled the clock back even 10 years from today, probably the best AI techniques 10 years ago wouldn't have been good enough to do a really good job. Even if you had, if you could implant Neuralink, and you had the physical interface working and it was compatible and that kind of stuff. Even 10 years ago, the difference between then and now in terms of how good AI is would make a really dramatic difference in how useful that implant was going to be today. And by the time they're able to, cross that threshold of something that's functional for a healthy human being, we're probably not going to be talking about 1,000 electrodes. They're probably going to be talking about 60,000 electrodes or something like that implanted at that point, maybe 1 million electrodes by that point. And it's definitely going to be the case that if you want to make the best use of 60,000 or 1 million electrodes to really milk the dynamic, bandwidth that's available out of that, it's going to take some pretty sophisticated AI to do a good job with that. Probably stuff we don't have today, but probably stuff we will have a lot more in 10 years, and it's going to help a lot with that problem.
Can you explain in a little more detail what the advancements in those neural network like training could look like? Well, I guess you don't even have to know what the reason would be, right? Like there could be some phenomenon occurring in the brain, and just because you have an advanced neural network ability to train the neural network, then you could learn a lot of stuff about the brain that you wouldn't be able to today. Is that true?
Well, if you're talking about from a research standpoint of trying to understand the brain and what it does, yeah, that's certainly true. I'm thinking more, when we're talking about Neuralink, I'm thinking about an implantable device where the objective of the device is to provide a high bandwidth output and maybe a high bandwidth input channel also to to a human being who's engaged volitionally in conversation, right? Like you want to say something and you want to understand something which is being said to you or that you're receiving. And Neuralink's ability to facilitate that in ways that like your five senses and your ability to speak or your ability to type can't. So there's kind of two aspects to this. One of them is the bandwidth, right? The direct bandwidth that you can get from a neural implant in principle is much, much larger than the bandwidth that you can get in through your eyes or your senses, and much higher, much, much higher than the bandwidth that you can express with your voice speaking or with your hands typing. Especially the typing thing that's an especially severe constraint right now. So that's one part of it. The other thing is like if you close the loop, it gives there's this other level of stuff which can happen where you've got signals going into the brain and you've got the brain's ability to respond directly to those signals and provide feedback directly back through the interface. So the brain itself is very plastic. It learns and it adapts really quickly. And existing brain-computer interfaces, they all take advantage of this to a greater or lesser extent. Somebody who receives a brain implant, you have to learn to use it. There's a training process that you go through. And the biological manifestation of that training process is that your brain tissue is reconfiguring to enable itself to do what you want to do as to the best of its ability with that interface, whether it's understand what's coming in or clearly express what it is that you want to send out. If you can close that loop tightly right at the level of the brain tissue, it's very likely that learning process is going to go much more quickly. It's going to be much more nuanced and adaptable and respond quickly. So AI techniques are allowing us to make the machine, this brain-computer interface has a brain on one side, it's got a computer on the other side. And AI techniques, the brain is already plastic and adaptive learning machine with a lot of bandwidth and an ability. So to get these two to really talk to one another, they have to learn a protocol. When you plug this, every human brain is unique, like fingerprints are unique, but even more unique than that. When you're born, your brain has a rough plan for like this part of your brain, which mostly comes from like your genetics determine the coarse wiring of your brain. Like the nerves from your eyes, they go to a particular part of your brain. The nerves from your ears, they go to another particular part of your brain. Your hands, all the muscles in your body, they go to a particular part of your brain. But when you're born, like very little of that. This is for human beings in particular. For some animals, this is different. But when you're born, very little of that neocortex is pre-programmed to do very many of those things at all, which is why, infants have no control of their arms or legs, very little volitional control of their arms and legs. They develop it really, really quickly, but it takes a lifetime to develop really nuanced control of all these things. And that's your brain. That's the gray matter in your brain, the part that's really adapting to the fact that the white matter, the wiring that is all in there, the contractor came in, they built the building, they ran all the cables and that kind of stuff. And now you've got some people in there programming the computers, and the computers are figuring out which wire connects to what and how they're going to control, all the functions in this building or whatever. I mean, the big wires, they are kind of, constrained. Like you kind of get a set of those. But one of the amazing things about mammals and human beings in particular, because our neocortex is so big and so many of our functions route through the neocortex, but almost all of that is incredibly plastic and reprogrammable. So, and luckily for the people who want to make brain-computer interfaces, that neocortex tissue, it's totally exposed on the surface of the brain, just underneath the skull. So we can get access directly to all that wiring. So when you build it's very likely. You can't, if you had to do a thing where for a particular user, like say you want to build interface where a person can think sentences, thoughts, that kind of stuff, and the external system interprets it, but you're not going to rely on the brain's ability to adapt at all, right? In that case, you have to figure out which neuron is for the word the and which neuron is for the word, and so on. And unfortunately, the brain doesn't organize words in that simple kind of sense even. It's not like you have a neuron per word or whatever the deal is. It's much more complicated than that. So if you can't rely on the brain to adapt at all, you need just like so many electrodes and so much processing, so much time to like figure out what the existing hard wiring is, because it's different for every individual. I mean, we know, to a first approximation that a particular part of your brain is where most of the language stuff goes on. And the reason that that's where the language happens is because that's where the most important nerves in your body that are associated with language, that's where they terminate, in the cortex. So we can reliably say, well, your language center is in this part of your brain, but we can't reliably say for any single individual exactly which neuron is doing what thing. And so if we're sort of shotgunning a bunch of electrodes into the brain, which is kind of what Neuralink does, they don't figure out ahead of time with any specificity what any particular point in the brain is trying to do. They pick a section and they know that it roughly correlates with some function that they're interested in, whether it's motor or speech or vision. They put a bunch of electrons in there, and now the system has to learn how to talk to the brain, and the brain has to learn how to talk to the system. How well that learning works, like to what degree you are able to express nuance and express it quickly, to quickly express a sequence of thoughts, and with specificity and not, and accuracy, so there's not noise. That's a process that the brain half of the interface has to go through. And it's a process that the machine half of the interface also has to go through. Both sides have to learn to talk to one another. There's a handshake, and they're going to have to figure out what that protocol is. So, the brain has its learning algorithm, and we're not going to be able to mess with that very much. Luckily for people who build BCI interfaces, it's already an amazing algorithm. It's incredibly flexible. And especially in the case of like human beings, primates, this is probably true in dolphins and whales and stuff too. I don't know as much about them, but that tissue, it not only is it really flexible and really dense and really high capacity, but humans also have an amazing amount of volitional control. And we know all these tricks, like visualize this, imagine you're smelling that, imagine moving your arm, say in your head this word. I mean, we've got this very powerful imagination that we can use to learn to activate all these different parts of our brain in complicated ways. Primates can do this too, and that's why monkeys can learn monkey pong, right? It's, pigs can do it less, mice can do it less, and so on. Pretty much anything with a cortex, we know approximately how that goes. But animals with simpler brains and less of their brain dedicated to the cortex, their volition is less capable of expressing itself with complete plasticity. So humans are an extreme of that, which is great for planting these systems into brains. So now there's the other half. What does the machine side need to do? Well, we want a similarly plastic, similarly dynamic system on the machine side to make the most of that interface as quickly as possible. If you get a Neuralink implant and then you have to spend 20 years, learning, to use it before you can like move a mouse cursor around a screen, the ROI on that isn't as good as if you can implant this and people can get the mouse cursor control in hours or in a day or two. And if you want to be able to get, the mouse cursor is kind of low-hanging fruit. That's why they start with it, with primates, because we know with some amount of specificity what part of the brain controls like your right arm or whatever. And so if we look at some electrodes there in a primate's brain or whatever, and you do something that you engage in some activity that involves moving that right arm around, well, you can look at how the right arm moves around, and you can correlate that with the signals that you see coming out of the brain. You can figure out what the relationship is. That's what they did with monkey pong, right? The monkey starts out playing pong with a joystick, and they have a set of electrodes implanted in the part of the brain that's for the arm that's controlling the joystick. And they figure out what the correlation is between the signals in that part of the brain and how the joystick moves. So this is a really simple experiment in a sense, right? You watch how the monkey's brain tries to move the arm, you interpret those. And when your accuracy is good enough, like once you've trained the algorithm to the point where the algorithm can look at the brain tissue and predict accurately what the joystick is going to do, then what you can do is you unplug the joystick and you can just use the brain to control the thing. And that's what they did with monkey pawn. And this is an approach that's been used a couple of times. And that's one of the reasons why this motor cortex thing is a really popular way to do the experiment, because you can train an animal to do something physically with its body. You can monitor that. You can learn to interpret that. And that it makes for pretty simple. But imagine that what you want to do instead is do language, right? So that you have the equivalent of ChatGPT or some language interface AI that you're talking to directly. This is a much better interface than a keyboard and a mouse because it's much faster. Like almost everyone can speak much more quickly than they can type. And even for people who can type really, really fast, like if you try to speak quickly, especially if you try to speak in a really abbreviated fashion to someone well, people who've been living together for years and know each other really well, they can have complicated conversations with relatively few words because they look at context and that kind of stuff. And so the bandwidth that you get is going to go up a lot if you have more than, a keyboard has 50, 60 keys on it, something like that. And an action is choosing one of 60 keys. But when we speak, every word that comes out of your voice, even if you don't consider like tone and context and that kind of stuff, it's one of 20,000. Like your average adult frequently has a 20,000 word vocabulary that they use frequently. And most people my age, they've got 50,000 words that they can draw on. So this is a keyboard with 50,000 buttons. Like that's very high bandwidth. If you can hit several buttons a minute, that's a crazy high bandwidth. And that's kind of table stakes for where we want to get with Neuralink, is to have that kind of bandwidth so that the bandwidth coming out is hundreds of kilobits or something. The human brain is it's like one of these really big Google data centers. If you look at the processing capacity, there's really an enormous amount of processing capacity that every human being is carrying around inside their head. But you may be too young to remember this, but when I started, the first time I was able to get on the internet, I had a 100 baud modem, right? This is back when modems were, even before modems became popular. Like this is really, really slow, 100 baud modem, right? So imagine that you've got a Google data center and the only link out of it is like a single 300 baud modem link. Like that's the humans right now. That 300 baud is what we can talk. But there's all this computing capacity behind it, right? So, we have human language has, evolved to allow us to get the most value we can out of a relatively small number of words we're able to say. And we do this through all kinds of tricks. That some of them are signal processing, a lot of them are context and dictionary. Like when we're having a conversation and I'm not just saying words according to like some dictionary thing, but I'm modeling you and I'm modeling your model of me and I'm modeling, you can go around these loops, right? And we do this complicated modeling of each other when we have a conversation because it allows us to say more with fewer words because our pipe is so small and we have so much we want to say, right? Neuralink is at a real fundamental level, it's trying to break that thing so that instead of having a 100 baud modem, you have a 10 megabit cable link, or 100 megabit cable link or something like that. Vision input is a little bit easier. Vision is close to a megabit. So, the thing is you can only, human vision is designed to recognize certain kinds of things. So you can only encode so much visually. Like a human watching a soccer game can see a whole lot of things going on. You can watch a room full of kids playing and extract a lot of meaning. But if you're reading text, it's kind of slow, because your attention focuses from word to word to letter for most people as they go. So even though in principle, the bandwidth coming into your eyes is really high, as soon as you move away from naturalistic phenomena, like objects moving around in the real world, and we get to these abstract things like words on paper, it slows down. tremendously, right? And Neuralink can potentially break all of those gaps because it can go around your visual cortex's need to see kids and trees, right? It can, your visual cortex it's not great with really abstracted inputs, and text is highly abstracted. And so reading is slow. Reading is super slow compared to a lot of other things that we can do. That's why a picture's worth 1,000 words, right? Because it just takes a lot of words to express what you can see in a glance if the thing you're looking at is some natural phenomenon that people know how to interpret easily, right? If you're looking at noise on a TV screen, like a staticky channel, that might be megabits of content, but you're incapable of absorbing it because your visual cortex is not organized to grab, noisy data off a screen and turn it into something. But AI is going to be really important for making that interface work, because both sides of that interface have to learn to talk to each other, and that you have to do that from scratch every time for every single human who gets an implant. So we want those algorithms to be efficient. We want them to be really high bandwidth. We want them to be quick to learn. We want them to automatically adapt, because your brain is constantly remodeling itself. Every time you go to sleep, you wake up in the next morning and your brain is different. Like the functions in your brain that do things, they've all migrated slightly, a little to the left, a little to the right. They've reallocated a whole bunch of stuff. And a brain computer interface is going to have to be adaptive enough that it can keep up with your brain's constant imperative to remodel itself.
It's interesting that you had said you want to make it like it's a small pipe, but you want to make it much larger. With Elon was talking about how that communication is like a straw. It's going through a straw right now, and he wanted.
Yeah, it's nothing. It's shockingly low. I mean, it's like, you imagine one of these warehouse-sized Google data centers worth of processing capacity, because that's what brains have. If you're talking about CPUs, certainly that's what a human brain has. And yet one single dial-up line, 300 baud coming out of it, like that's all the communication it's got, right? It's amazing that we can make good use of it. And of course we end up in this space because we start from, evolution started out with no language. The fact that we adapted language, that we have it at all, and that it's so useful is a testament to the utility of even a little bit of communication when you have almost none. Mm-hmm. But human ability to communicate is severely, severely constrained by our IO limitations.
And that evolution will just accelerate with all the advancements in AI, and then with Neuralink too. Like we'll be able to communicate even faster and more efficiently than the rate of change was before, right?
Yeah, that's the idea. There is kind of an organization to the brain of an adult human being, which it comes to after a lifetime of experience. And, in the case of me and you, we got to this point in our lives without having a Neuralink. So, if we're not going to relearn all of that stuff from scratch, we are to some extent, adults like you and me, we're going to be constrained by the patterns our brain already learned and the way it already organizes itself, not having Neuralink. So people who grow up with Neuralink, they're very likely to have a very different set of constraints, and they're very likely to be able to have much higher bandwidth than an adult implanted with this. Even if you were 10 years old when you got it, as opposed to 20 years old when you got it, and 20 would be way better than being 30, right? In terms of the fidelity that you'll be able to get to. But so there are definitely organizational constraints, because the human brain is really plastic, but it's not infinitely plastic. It has to reorganize itself according to the stimuli. When it reorganizes, it's not like you can go to bed and you go into a coma for a month while your brain reorganizes itself. You got to be able to wake up in the middle of the night and run from a lion if you have to, right? So every single point of change, your brain has to, all of your mental functions, they have to remain functional as they adapt. It's not like when we remodel a house and, the owners can move out and then you tear everything down a month later, maybe, or 2 months later, or, if you're a normal contractor, 6 months later, you actually get your house back and it's working again, right? The brain has to stay functional all the time. So that means that, if you're an adult and your brain is built a certain way, then the foundational functions of the brain, they can only change so fast. So if we're doing a version of Neuralink that's really trying to get access to those foundational things, and you would like to remodel those foundational things in order to make it, what the brain is doing, better suited to what Neuralink is, to the purpose of using Neuralink effectively, that's going to take time. It takes much less time for a 10-year-old than it's going to take for a 40-year-old.
So when somebody has sleep paralysis, or they're dreaming, or they're lucid dreaming, is it known like why? Yeah, is it known why they're paralyzed, or why they're not able to like have a lot of their functions?
Well, in general, yeah, so sleep paralysis it's a side effect of the persistence of your motor cortex disconnect. So when you sleep at night, you dream, and in your, like, one of the things that happens in your dreams is your brain tries to move your arms and legs around. Like, it will attempt to act out the things that you're dreaming about. And as a presumably protective function, your brain disconnects your motor cortex from your body when you go to sleep, so you're not thrashing around in bed. This is just a normal function. Everybody's got it. So there are various kinds of dysfunctions of this switch that can occur. They're rare, but they do occur. And one of them is that the switch cannot turn on when you go to sleep, or it can be slow to turn on. So those people, they move around a lot in their sleep. Some of them get up and walk around in their sleep, right? There are manifestations of sleepwalking that are literally like, this thing isn't disconnecting the way that it should. The other one is what we call sleep paralysis, which is you wake up and the switch is still on. Your brain is still disconnected from your body, but you have become conscious. So then you go to move your body and it doesn't move because the switch hasn't disconnected yet. And people who experience this, they experience it as being paralyzed. And I guess there's this, I don't know if it's a hallucination. There's this kind of way of experiencing this, which is that it feels like someone is sitting, or you have a great weight on you holding you down and you are unable to move. So of course, people experiencing this, they're waking up in the middle of the night, they're kind of groggy, they're just emerging from a dream or something like that, and their body's not moving, right? And suddenly they have this kind of panicky moment. And your intuition immediately goes to, I'm being held down, right? Like, you can go back hundreds of years and you can find people writing in their diaries about how, like, they woke up in the middle of the night and a demon was sitting on them or whatnot. And a minute later, the demon vanishes, right? And they get their movement back after the switch like reconnects the way that it's supposed to, and you get back. So those are dysfunctions of sleep paralysis. That's what you're talking about, right?
Yeah, I'm like, again, in shock at your breadth of knowledge. Just like, you happen to know this. Let's see. So Michael asked on Twitter, can nanotechnology be used as a part of Neuralink, specifically as electrical conductors, computing processors, or as a biochemical interface with the human physiology?
Nanotechnology is super well suited to assisting us in making effective brain-computer interfaces. In a sense, the single biggest challenge of brain-computer interfaces is that the things we want to interface to are so small, and we are so big, and all of the things we make are so big by comparison. So nanotechnology, I mean, the word gets used a lot of different ways. Once upon a time when it was first coined, it meant, molecule-size complex machines. And if you, certainly if we had those would be incredibly useful. In fact, like if we had mature nanotechnology, brain computer interface is trivial. Like it becomes a very simple problem to to overcome. Like most of the problems of that we really struggle with are in large part because the smallest devices that we can make flexibly and that we can control well aren't all that small. And the components we want to try to talk to in the brain are really, really small. We were talking about how, the needle size that they inject that Neuralink is currently using is on the order of 40 microns. And 40 microns is the width of an entire neurocortical column with like 100 neurons in it, right? So I don't know. It's like, imagine that I'm trying to build I'm going into a data center and I want to shove a sensor down into the data center, but the sensor's the size of a whole rack of computers, right? So I'm going to ram it down through the ceiling and, the racks are just going to have to move out of the way, right? It's, the things we would like to be able to talk to are really, really small. And it's, we have a hard time. So another way of interpreting nanotech, which is the way the term gets used more today, is talking about making things with a degree of precision and control that we are manipulating the structures down below the scale of about 100 nanometers or so. That's just generally what people consider nanoscale, right? Once you get below 100 nanometers. So everything that we can do at less than 100 nanometers, like every significant manufacturing technology that we have that will let us get down below that scale, is a potential contributor to brain-computer interfaces. So in that sense, we have nanotechnology today. We have many technologies that can get down to that scale. Like we can make transistors really small. An interesting thing to consider is the possibility that a somewhat more mature version of Neuralink today, right? Neuralink today, all of the electronics are in the little puck thing that gets implanted, in the cranium. And then the probes that go down, they're just wires. I mean, they're complicated, super, super skinny wires, but it's just a wire. It doesn't have any active components in it. It's an insulator. It exposes the conductor at some point near the tip, and that's all there is. But imagine that you could embed an amplifier in that so that it was an active component, not just a passive component, so that the wire that goes back up to the electronics is a controlled impedance transmission line, and not just every wire is a transmission line, but if you can do a controlled impedance transmission line, you can get more signal more reliably at lower sensitivities. You can transmit it farther with less degradation of signal fidelity. And to do that really well, you want to be able to embed an amplifier right in the tip, like right where the wire is. Well, physics says you can do that. I mean, we make transistors in integrated circuits now. We can build amplifiers that are smaller than 40 microns, much smaller than 40 microns. So in principle, you could make an amplifier using existing integrated circuit technology and stick it on the end of one of these things. And it would be as small as the tip of one of these probes that we're sticking in the brain right now. And you could have all kinds of signal processing right down there. And then you could do the pre-processing right at the end and go. Now, even if we're not talking about complicated machines like that, electronic machines, on the scale of the 1 micron scale of the end of the tip of one of these things, you could imagine, for instance, one of the things we have right now is if you look at the 100 nanometer scale of one of these probe tips, it's like a telephone pole being shoved into a complicated shove a telephone pole into a bush, right? That's a probe going into your brain right now, where all of the leaves are, neurons or synapses and that kind of stuff. Like the probe itself is big and crude compared to the structure that you're trying to get access to. But the fact that cells can organize complicated structures at much, much finer scales than we can build the probes to right now says physics allows that to happen. It's a matter of us working out the manufacturing technique. So nanotubes are something we know how to make now. They're super useful. Nanotubes, so nanotubes There are lots of different ways to make them. Basically, anytime you make a wire or a tube, you take a sheet and you fold it on a molecular scale, and you get it down to the order of 10 or 15 nanometers or something like that, or even smaller. You can get really small. We call those nanotubes. And if you make them if you use carbon as a substrate, carbon is a semiconductor, just like silicon is a semiconductor. And if you fabricate a nanotube, you can take a sheet of graphite. You can do this with silicon too. It's just easier with carbon. You can make a single layer nanotube or multi-layer nanotubes. If you make multi-layer nanotubes, then where you take the sheet of graphite and you roll it in a tube. And then if you look at graphite, it has a hexagonal pattern. You get like 6 carbon. Well, it's a sheet, and the carbons embedded in the sheet, they have 3 links to other carbons in their layer. And the 4th link, every carbons all have 4 bonds. Crystalline carbon has 4 bonds. And so when you make graphite, every crystalline carbon has 3 bonds that connect to 3 neighbors. And if you do that across a grid, you get this hexagonal pattern, these repeating hexagons. And every other carbon atom, its 4th bond goes up or down. So, if you go along the molecule, you get, carbon spare bond up, carbon spare bond down, carbon spare bond up. So you take 2 layers of graphite and you sandwich them against one another so that the ups from one connect to the downs on the other and the downs from both. Well, that's what graphite is. So you get graphite, you look at the structure of graphite, that's how it's built. So the thing is, graphite looks kind of like chicken wire, right? If you roll out chicken wire, it's used for fencing on farms or whatnot. It's this hexagonal pattern of wires. You roll it. Well, you could imagine that if you roll up this hexagon, you can roll it up a bunch of different ways. Like, if the hexagons go across this way, you can just roll it and match one against another. And that makes a really strong pattern that has a certain alignment. There's a certain amount of stress between the layers because each subsequent layer is a little bit larger. So they don't match perfectly. You get stress inside the structure, and you can slightly tweak the way that these layers roll against one another and vary the crystal structure that forms between the adjacent layers as you tweak these things. And you can generate almost any kind of band gap that you want. Band gap is an electronic property that we use that defines the electrical characteristics. So you can make carbon nanotubes into semiconductors with whatever band gap that you want, and they can become active electronic components. Like, all of this is within the realm of possibility. It's been demonstrated. There are companies now working on trying to make integrated circuits where the transistors are, nanotube layers that are deposited down on substrates that are made with more conventional semiconductor manufacturing techniques. So now, you can also do experiments in the lab where you get single carbon nanotubes, you build them at some kind of scale, and you tweak their electronic properties. And it doesn't have to just be graphite. There are lots of other materials that you can use also. Graphite's popular. It's very flexible. We know how to make it. It's a semiconductor. It's really strong. It's got a lot of really great properties for doing this kind of stuff. But one of the things you get a really small wire out of this, because graphite is conductive. You can tweak the conduction also by doping it or by changing the crystal structure. Carbon nanotubes are potentially orders of magnitude smaller than the smallest wires that we can build today. So this, like I said, it's the probe on a Neuralink today is like a telephone pole jabbed into a bush, right? And the carbon nanotubes are much closer to the scale of wires coming off of that telephone pole. So, like, if you wanted to connect with more fidelity, resolution, proximity to all of the cells and synapses and axons and dendrites that are in this tissue that you're trying to interface to, well, in principle, a carbon nanotube can go right down to a particular synapse and sample it directly. It could go right down to a particular branch of a dendrite or an axon, and you could sample that directly. So, when we get the control, and we will eventually get the control to be able to make these things work, the way that we want them to be able to build structures at that scale. Yeah, that's going to be amazing for brain computer interfaces, because now you'll be talking about, I mean, you might still at some scale be shoving a telephone pole into a bush, but once you get the telephone pole down there, you will have a very large number of very smart little wires come out of that telephone pole that will be able to interface to the surrounding nerve tissue with a lot of fidelity and precision that will give you much better signal characteristics for both your input and your output on that. So yeah, nanotechnology is already to some extent playing a role. I mean, we talked about how they're trying to use amorphous silicon carbide as an insulator for these electrodes right now. I don't know if they're doing that right now, if they're just looking at it, but if you're probably talking about a layer of silicon carbide, which is on the order of nanometers thick, in order to make that work. Because of the characteristics of silicon carbide, you can't put a very thick layer on and still use it as a insulator for a flexible electrode. So in certain respects, there are already going to be aspects of what they're doing that are nanotech. And certainly the ICs these days are getting really, really close to nanotech. If you're, when we talk about the TSM, the process they're using right now is, 20 so-called 28 nanometer integrated circuits, which means that the smallest transistors, to a first approximation, the terminology is, it used to be that when you said, 100 nanometer or 90 nanometer or 300 nanometer, like back when we were at that scale, it was really true that when you looked at a transistor, the smallest feature was like 300 nanometers or whatever. As we've gotten smaller and the shape of transistors and ICs has gotten more complicated, that simple metric we used to use doesn't work as well. And it is now the case that when you talk about a 5 nanometer silicon process, you're no longer talking about a process where the smallest transistor component is 5 nanometers. It's roughly approximate to that, but that's no longer true. But, we are talking about single digit nanometer scale minimum feature sizes for the electronics that are going into this. And of course, Neuralink, it wouldn't be possible without the nanotechnology of semiconductors that we're using in it right now, because you have to get a certain level of processing capability. You have to be able to do it with a certain level of efficiency. You have to be able to do it in a certain package size. And, the nanotechnology that we enjoy with semiconductor processes today is totally critical to making what we do with nanotech, what we do with Neuralink possible now. And it's going to become even more important going forward. We will have 1 nanometer or sub-nanometer scale semiconductors by the time Neuralink is really a mature technology, and it'll get used for this kind of stuff. And I wouldn't be surprised if a significant part of the technology isn't making really small ICs that go on the ends of the probe tips that get injected directly into the tissue, so that you can get more IO with better signal to noise ratio than you can get by just sticking a telephone pole in a bush, right?
So this is James Dauma's prediction for Neuralink.
It's always, we're going to use the technology we have at hand to make it as good as we can. And Neuralink is today, and is going to continue to be for quite a long time, limited by the limits of material science. And nanotechnology is the bleeding edge of material science.
Sure. Okay, so I have this thing that I want to share. Can you see my screen?
Mm-hmm. Well, it's kind of small. Let's see.
Oh, it's small?
Well, I could stretch my window a little larger. Okay, that's better. Go ahead.
Okay. So Warren Redlick posted this poll on Twitter, and then he said, what's the greatest risk of artificial intelligence? And then you responded with this, and I'm going to say, let's choose the expectation value of impact. So total area under the curve, I guess, of impact. What do you think is the greatest risk of AI?
I think the greatest risk is it spoils us to the point. What's it? Elon has some expression like it's like the fear that human society ends not with a bang, but with a whimper. And he said something like a whimper in adult diapers or whatever. That I think the biggest risk, the biggest kind of intermediate duration risk that we have is that we get all we want and we stop caring, right? Like as in terms of area under the curve, right? Like human society, if humans stop caring, if we stop working, if we stop trying to make the world better, if we stop trying to help each other, you know, if society can, you know, if people can individually get what they want out of life and they don't need other people, they don't have to interact with other people. You can live in your own bubble where you just have all the things you want and everything in the bubble caters to you. Like that is a kind of death of society. And, you know, and it does die in adult diapers because you know, the incentive for having kids, having kids is a super risky undertaking, right? It takes a lot of time. You get really invested in it. You know, if people are honest with themselves, there's no guarantee that it's going to turn out great for you. It might turn out great. It turns out great for a lot of people, but there are a lot of people it doesn't turn out great for. And, you know, if you can live in your virtual reality fantasy and, you know, you can have exactly the kid you want if you want to have kids, right? The computer will fabricate the kid that you want in your fantasy world, and you can have the experience of raising them in that world if you want to, right? You don't have to take any risks. You get everything you want, right? That's area under the curve in terms of like actual risk, likelihood of outcome. That's the thing I think is probably the biggest risk. It's not that we do something terrible, it's that we get everything we want and stop striving because of that. And that at some point, not long after that, you know, that's my favorite answer to the Fermi paradox, by the way. The Fermi paradox is Enrico Fermi the story behind it. The reason it's called the Fermi paradox is because Enrico Fermi first posed this question, and apparently he did it over lunch with some other guys at, I forget where it was. I think it might have happened at the Manhattan Project. But anyway, there's a bunch of Nobel Prize winners sitting around the table, and they're talking about how big the universe is and like what the probability is of life being out there and all that kind of stuff. And Fermi says, "Where are they?" Right? Which is, it sounds like a simple question, but there's a really profound reality that underlies it, which is the universe is really, really astoundingly, mind-bogglingly big. I mean, you think the Earth is big? The Earth is nothing compared to the scale of the universe. It's really unbelievably big. And it's been out there for 13 billion years. Like, we're nowhere near the first on the scene. So if there's any likelihood to intelligent life at all, the galaxy, I'm assuming they don't die off quickly, right? That's another thing. Like if intelligent life arises only to vanish 1,000 years later, well, yeah, there aren't going to be any out there because they never survive long enough to get out there. And there are lots of different answers that have been posed to the Fermi paradox, but the thing that seems most likely to me is that is that before you become a Kardashev 1 civilization, everybody gets what they want and they don't have to do anything for it. And, we're the product of natural evolution. Our instinct is to cover our needs and be grateful for that. Right. Once we were talking about the limbic system and how your neocortex is kind of like, your limbic system is kind of like this dumb brute, just wants things. Right. And your neocortex is like this, this amazing tool that your limbic system has, and your limbic system uses it to get what it wants out of the world. Well, if we get the tertiary cortex, and tertiary cortex is dramatically more capable than our neocortex is, then our limbic system is just going to get what it wants. And, one of the things you can observe about people is once they've got what they want, they just watch the Flintstones, right? They watch, so anyway, that might be the fate of civilizations, right? So that's what I think the big risk is. I think the big risk is that we get what we want, right? And that, you know, the striving that all the generations before us, well, in Western civilization, we think of, like man struggling against nature to achieve, you know, a great purposes for himself, his species, his family, his country. And so these are the higher callings that we work towards, whether it's, you know, beating cancer or feeding everybody or ending war, you know, whatever these things, these are all these great things. But you know, what happens when you get all that, right? You don't have cancer and people don't die and there is no war. There's no, you know, you get to a post-scarcity civilization. That means that nothing's scarce. Like everything anybody wants, they can have. And once upon a time, you know, the counter argument to post-scarcity civilizations was, well, people will still be scarce, right? In a post-scarcity civilization, you might have all the material stuff you want. You still got a finite number of people. Like every single person has one person completely dedicated to them, which is them, right? But AI totally solves that problem. You know, if there are machines dedicated to being your friends and they're as smart as people, they can be every bit as funny, interactive. They can mimic any person that you want with perfect fidelity because they're a superset of that person. Now, all of a sudden, there's nothing scarce, right? Everything is abundant and there's nothing that you have to work for. You can have anything you want at any point in your life and you don't have to do anything for it except want it, right? Like you know, in a very real sense, that's the end game for technology. And an important question is, now what, when you get to that point?
Yeah, I see. I had thought that when Elon brought up this this claim about like people or civilization dying off with a whimper, I thought it was primarily based off of like people are continuing to live longer and longer and they're having fewer and fewer kids. But actually it's both what you're describing and also like this whole people living longer and lower birth rate.
Yeah.
That would cause the whimper.
That's the extreme case, right? And people live infinitely long. There's arbitrarily low birth rate. You know, the universe has been around for 13 billion years. The Earth formed 4.5 billion years ago or so. The first bacterial life is 1 billion years ago, something like that. We got complex multicellular stuff on the order of a couple 100 million years ago. We had the Cambrian explosion, that kind of stuff. Dinosaurs are 60 million years ago. Like the humans have been around as a species, you know, most people would say on the order of 1 million years before we draw. So like for 1 million years, there have been people here. For at least hundreds of thousands of years, people have had language and societies as complicated as the societies and languages that we have today. For 100,000 years, we were still basically aborigines, right? And then, you know, in 1400, we had the Renaissance and we've been on, you know, like a train to the future ever since then. And here we are, and it's just getting faster and faster and faster. You know, so there's all of this history behind us bringing us to this point, and we're really, really close to just like everything humans ever wanted, and we're getting there really quickly. And it's worth asking, you know, like where does that leave you when you get there? Train's pulling into the station now, right? And you know, we got to decide where we're going to go when we get off this train.
Yeah. It seems like there's definitely like a certain level of fulfillment that's needed after like the initial basic things are covered, basic needs are covered. It's like that Maslow's hierarchy of needs, right? Where it's like the food and sleep and shelter, and then after that, the fulfillment. Right. It's like a lot of people now, they're just retired early, and there's no more like Siobhan posted this from Neuralink. She was like, yeah, people need quests to pursue. And
yeah. Is life about the main quest or the side quests? Yeah.
Yeah. But it's like a lot of the Silicon Valley tech nerds, or anybody nowadays with all these different creator tools, anybody could hit that financial escape velocity super early. And then it's like, what do you do? There needs to be something.
Yeah, that's one of the things that makes Elon such an anomaly, right? Is that it is like, the common path is what Jeff Bezos did, right? Or what Bill Gates did. You get your $100 billion and then you disengage. Like, why should you keep suffering? Why should you struggle against all these things? Haven't you done enough? Don't you deserve to like enjoy your life now? You've done plenty for people. Just relax. Life is short. You struggled for so long, and that's a super attractive, people who get to that point and they have an obsession which is strong enough to keep them productive way past the point that they have everything they need. I think they're a rare breed. And, one of the solutions potentially to this dilemma that I just, posited about us getting everything we want and it being our undoing is either culturally or, with some sort of genetic intervention, making people making everybody like Elon, right? So you just don't stop. Right? You're never satisfied. You always want more, right? There's good sides and bad sides to that, right? Like if you're never satisfied, right, that can also lead to all kinds of pathologies and the destabilization of society. Like even a relatively small number of people who are unsatisfiable can be really destructive to a society if they have influence. But on some level, if everybody or virtually everybody is easily enough satisfied that we soon get to a point where we can satisfy them, that itself, that's also a really big problem, potentially. But
Sure.
anyway, so we're going a long way with Warren's question. Like I could come up with all kinds of other potential downsides to AI. The reason I asked his question is because I've literally heard 100 different plausible, problems that AI can do. Societies are really complicated things. They're really, really complicated things. And they're super dynamic and they evolve all the time. And every time you bring a new technology into society that messes with the dynamics, the stability of aspects of that society, you are, the society is going to undergo changes that some people in that society are going to see as very destructive and very negative thing. Other people might see them as really positive things. But so, AI is going to be the most powerful technology. Like a lot of people have said it's the last technology, right? It's a deep mind is right there in their motto. It's like solve intelligence and use it to solve everything else. And there's a sense in which that's really true, right? You solve intelligence, we're done. The whole human race can go on vacation now, right?
Yeah.
This was my second conversation with James. If you missed the first conversation, check it out here. And if you've already seen that one too, there's another video right here that YouTube's recommending specifically for you. Hope to see you at the next episode.